So good afternoon, everybody. Welcome to another joint astronomical Heidelberg astronomy colloquium. As always, this is the place to be on Tuesday afternoon in the middle of a hot summer. And thanks also to the Zoom audience to join us. Now we're, for the first time this semester, we're delving into the realms of dark matter. And we're very glad to have Anna Nierenberg to say something about this. And Anna's host, Joachim, to make the formal introduction.
Thank you. It's my pleasure and privilege to introduce Professor Anna Nierenberg, today's speaker in our Heidelberg Astrophysical Joint Colloquium. Anna got her bachelor education at the University of California, LA. In 2008, she moved on then north to the UC Santa Barbara and worked on her PhD with Tommaso Treu on dark matter satellites already, finished in 2014. She then moved to the University of Ohio State for 3 years as a postdoctoral fellow there. Came back to California, UC Irvine for a year. Then she got a NASA fellowship for the Jet Propulsion Lab in Pasadena for 2 years. And finally, in July 2020, she joined the faculty in UC Merced. There are lots of advantages living in California and being a member of the University of California system. One of them is getting access to Keck. So she was very successfully using Keck. She also got a lot of HST time and lately JWST time. So we're eager to look forward to your talk. And for those of you who don't know where Merced is, it's 2 hours east of San Francisco, of Santa Cruz, Monterey, so Cupertino. So it's a very nice location to be. So please, the stage is yours.
Thank you so much for that very kind introduction. So, yep, I'm going to talk about measuring the properties of dark matter with strong gravitational lensing. And I don't know, is it common here to ask questions during the lecture? Yeah, I'm very happy to answer any questions during the lecture. Love to clarify things. All right, so quick overview. I'm going to first give you the connection between gravitational lensing and dark matter. So what is the connection between these two things? An overview of some of the measurement techniques. I'll go through some recent results and then discuss future prospects. And Professor Wamsgans has, I put this in because the most frequently asked question since I've been here is, where is Merced, which is completely fair. So it's in the Central Valley of California here, indicated by this star. It's the newest University of California, so it's completely fair that many of us haven't heard of it. Founded in 2005, and particularly to try and attract students from this Central Valley, which is the agricultural heart of California. We have 9,000 undergraduate students and about 600 doctoral students, 50 in physics. Of course, you have to remember our PhD takes about 6 years, so we have about 10 per year in physics. Because we have the combined PhD masters. Some highlights are 90 minutes to Yosemite National Park, which I take advantage of. And then, of course, the most important thing, access to Keck. All right. So dark matter is one of the biggest mysteries of modern physics. I don't think it's an American hyperbole to say that. We have ordinary, this is a very scientific pie chart I made, by the way. So ordinary matter, I think we all are familiar in this audience. Ordinary matter, things like electrons, protons, neutrinos, the things that make up gas, stars, planets, and humans, makes up about 20 to 30% of the matter in the universe. And dark matter is the rest, unknown. And obviously, this is a major hole in the standard model of physics. And, you know, I think dark matter explains many phenomena. We're all familiar, I think, here with the rotation curves, the anomalous rotation curves, the fact that stars orbit in the outskirts of galaxies faster than you can explain with baryonic matter. But there's other important indicators of the existence of dark matter, including the motion of galaxies in groups and clusters. And I think one of the strongest, in my opinion, is the cosmic microwave background. The fact that you can't fit this third peak in the cosmic microwave background unless you have a significant component of matter that doesn't interact significantly electromagnetically. So there's a lot of really compelling evidence that dark matter is there and an important part of our universe. So here's our cartoon picture of what we think, or not a cartoon, sorry, this is a simulation. I'm going to show a cartoon in a second. So this is a simulation of what we think dark matter would look like if we could see it. So this is a cosmological simulation. So we're seeing the cosmic web here. Lighter areas are areas with high densities of dark matter. We think that the universe has this filamentary structure where there's large densities. And if you could see it in 3D, it would look like sort of like soap bubbles with big voids in the middle. And this is caused by the combined effects of the expansion pushing space apart with the gravitational effects of the dark matter collapsing. So we get these thin sheets. And if we zoom in on a region which has a lot of dark matter, so zoom, zoom, zoom to here, you can see, broadly speaking, we have this large elliptical overdensity of dark matter represented by this yellow haze. And if we make a cartoon of that, it would be this elliptical watermelon shaped thing. So we call this a dark matter halo. This is a self-gravitating dark matter structure within which sits the gas and stars. One really important feature of the dark matter halo is that it's much more extended than the gas and stars are. And this has to be true in order to match the rotation curve observations, in which the stars out far from the disk are orbiting faster than we expect. The only way that can be true is if this dark matter halo is really extended compared to the galaxy gas and stars. And that actually puts some limits on how much dark matter can interact with itself, the fact that the halo has to be so much more extended than the gas and stars. Okay, so we have many dark matter candidates, and they're motivated by solving holes in the standard model. So we have other issues with the standard model, not just dark matter. So it'd be really great if we could just kill two birds with one stone. We could have dark matter, and we could also, for instance, solve the strong charge parity violation problem. So here are a few examples. Weakly interacting massive particles, or WIMPs, is sort of the default dark matter. That's what everyone kind of thinks of. That's nice because it has a really nice order of magnitude calculation you can do that gives you the right abundance of dark matter. Stereoneutrinos are an example. They could explain neutrino masses. Again, I already mentioned axions, or this fuzzy dark matter. This is a simulation of axion dark matter. You can see the dark matter halo here, and this is kind of what the cosmic web would look like in axion dark matter. And then primordial black holes are nice because they would explain some of these LIGO detections of intermediate mass black holes merging, which are not expected by our previous knowledge of stellar physics. So can we test these models? Can we tell which one of these many ideas is the actual dark matter? So here's a key thing, which is that the different dark matter models are producing different dark matter halos. On the left is a simulation of a Milky Way mass halo with cold dark matter, which is the weakly interacting massive particle. And I'll explain a little bit about why we use these temperature definitions in a second. So we have the cold dark matter model on the left and the warm dark matter model on the right, which would be caused, for instance, by a sterile neutrino dark matter particle, which could explain, for instance, like I said, the neutrino masses. So we can see these pictures look very different. On the left, we have a large halo surrounded by many smaller galaxies we call subhalos. These are dark matter halos that are gravitationally bound to a larger halo. On the right, in the warm dark matter case, we have many fewer halos. And this is just like, we're just empirically observing this fact right now. Okay, so what is the connection between the particle properties here and the number of halos? Let's take a look, because remember, a particle here, even in the cold dark matter case, is maybe giga-electron volts. It's 1,000 times more massive than a proton. And here in the warm dark matter case, we have maybe a keV scale, something 1,000 times less massive than a proton. So how could a tiny difference in the particle mass affect the present day halos, especially if the particles don't particularly interact other than gravitationally? That's because of how structure grows. So nowadays, halos are very large. But of course, we know early in the universe, everything was smaller. The universe was much more compact, and all of the fluctuations in the density field were tiny. So immediately after inflation, we have some small fluctuations, at least this is the current theory, and those are what grow to be the present day halos we see. So what happens is if the velocity distribution of your dark matter particles is higher, at these early times, you can erase some of the small scale structure. And that's what's getting mapped onto erasing the small scale structure at present day. So it's the fact that the density field and everything was so much more compact, fluctuations were smaller, that this relatively small difference in the particle mass can make a huge difference at present day. So warmer, we call it a warmer temperature because those particles are created with a higher average velocity than the colder particle. And we can quantify some of these changes using a couple of parameters that are very simple. We have a broad parameter space, but generally we can approximate most of these effects with a couple of things. And one of them is the half-mode mass. So this is the characteristic cutoff scale where you have less structure than you do in cold dark matter. So this plot shows the projected number of halos per square kiloparsec. So it's just a projected number density versus the halo mass. And if we look at the black line, this is the cold dark matter case. So you could see the cold dark matter mass function. I've wrote the equation down here. It's just a simple power law with no break in it. And this power law continues way, way off the screen, probably down to masses we think of about 10 to the minus 9. That would be the theoretical prediction for dark matter halos, that they would form down to planet masses if cold dark matter is correct. In contrast, a lot of these warm dark matter models have a turnover here. So they have a mass scale where it's suppressed, and that's because of this velocity distribution at early times. And we call this scale where you have about half the amount of structure as you would have had in cold dark matter. That's called the half-mode mass. Yes, so if you have a half-mode mass that's higher, then you deviate from cold dark matter at higher halo masses. In this case, we show a half-mode mass of 10 to the 7 solar masses, and you can see around 10 to the 7, we start to have a significant deviation from the cold dark matter model. But as I play around with things like my particle mass or my creation mechanism, I can have almost a continuous mapping of particle properties onto half-mode mass. Another thing that gets affected significantly is the concentration of the halos. So here's an NFW density profile here. Rho of R is proportional to the density at the scale radius, and you can see everything goes as R over the scale radius here. So that relationship between the virial radius and the scale radius is the concentration, and it just tells you how much of that halo mass is concentrated in the very center of the halo. Warm dark matter models form later at a fixed mass, and therefore tend to be less concentrated. And here's a simulation from Macho et al. 2013 showing the deviation in the concentration of the halo compared to the cold dark matter model equivalent mass. You can see they become systematically less concentrated, particularly as you get far from the half-mode mass, which in this case was quite high, but this shows a proof of concept here. So if we can measure these properties, then we can learn about dark matter. Traditionally, people have used galaxies as tracers of dark matter. And a classic example, a classic result from this is something called the missing satellite problem. If you look at the galaxies that are orbiting around the Milky Way, there's maybe a few hundred, maybe if you correct for completeness, several hundred or 1,000, which is significantly less than the cold dark matter prediction, which predicts many, many, many dark matter halos. But of course, we know it's very possible that there could be dark matter halos which just don't have stars in them. So if we want to measure these properties, and I can show that here, this is a dark matter prediction for the mass function of the Milky Way satellites, their halos. And then this is the observed mass function of the satellites using their rotation curve. So what you could just do is do what Nadler et al. 2020 did, and they took a look at, they just said, let's say CDM is correct, then at some mass scale, there must be just no stars in the halos. And they found that that would have to be based on their measurement of DES satellites, somewhere around 10 to the 8. So if cold dark matter is correct, somewhere around halo masses of about 10 to the 8, you stop having galaxies in your dark matter halos. So if you want to test the properties of dark matter, whether CDM or warm dark matter, you need to go below this mass scale to be free from the effects of baryons and also to test some of these dark matter models I'm discussing. So how do we do that? This is where strong gravitational lensing comes in. So here's an example of a strong gravitational lens. We have a single background galaxy here, this blue, shown in blue here, and it's being multiply imaged by this group of galaxies. So this is a strong gravitational lens. What's important is that low mass perturbers, so significantly lower mass than the main dark matter halo, can cause deflections and magnifications, and that's what we're seeing here. So we're seeing that this image, which should just be a long arc like this, is being split by this G4 galaxy here. So the low mass perturbers cause both deflections and magnifications. So if we look at the gravitational potential, this is the key thing for lensing. The gravitational potential is just the projected integral of the Newtonian potential for a point source, just GMM over R. And we have some lensing distances in here to get the optics in, but this is the gravitational potential. And we can see the deflection is related. So the amount of the light is getting distorted compared is proportional to the first derivative of the potential. And then the magnification is proportional to the second derivative of the potential. So we can detect perturbations as deviations from a single halo model. And this is a famous result from Simona Vegetti et al. Showing this method applied to a nice gravitational lens here. Here's the data. And she looked at how this lens was being distorted, and she compared it to a smooth mass distribution and found that there had to be a perturbing dark matter halo here. And it's, in this case, we cannot see the perturber by eye. That is absolutely not detected optically. So we're only seeing its effect on the fact that of this asymmetry here and how this feature is being lensed. And it really requires, and this full gravitational lensing technique reveals this. So there's some real strengths to using lensing to measure dark matter. One of them is that we don't depend on the halos containing baryons. We don't have to worry about whether or not a given halo has baryons. We can test the dark matter model regardless. Another is that we can measure these low mass halo properties, these perturber properties, at a range of cosmological distances and in different environments, so outside of the Milky Way. And we can make our measurement even more sensitive to low mass halos by starting to look at smaller and smaller sources. So this kind of large extended galaxy I showed earlier, that's sensitive currently to about 10 to the 8 solar mass halos, right at that junction where we're interested in looking for purely dark matter halos. Although depending on the resolution of the telescope, so things like the next generation 30-meter telescopes and possibly VLBI can improve the sensitivity of using galaxy sources. Unresolved sources, though, allow you to push down to even lower masses. And this can be understood with this amazing illustration I made of a dark matter cat. If you imagine you have a large beam of light and you have your dark matter cat lensing it, if the cat is large relative to the beam, it's just going to have a larger effect. It's really that simple. Like, you will have a larger relative effect on the magnification if your source is smaller. That means that unresolved sources, because they're smaller, are just systematically tend to be sensitive to lower mass perturbations. So currently, with our current methods, we're sensitive down to about 6.5 solar masses. Of course, both methods are complementary. The nice thing about this method is you can actually see the location of the perturbation, whereas in the unresolved source lensing, we cannot. So we really need both to get the best possible constraint on dark matter. I'm going to focus on our results using unresolved sources. Okay, so we saw a very nice illustration in a resolved source with a galaxy. So the question is, how do we know we have a magnification by a dark matter halo if we have an unresolved source? And here's how we do it. We take a look. Here's 4 images of a lensed background quasar with the foreground galaxy. And this is a Hubble image. So what you can see here is the image positions are very well fit by a 1 halo model lens. So here we have the 4 image positions. We can match those arbitrarily well, but the 1 halo model fit, so that would be just a single lens with none of that clumpy structure, it does not match the flux ratios that we see. So here, this flux is significantly demagnified relative to this one, and in my 1 halo model, they're the same. So in order to reproduce these flux ratios, so the relative magnifications of these two images, I need a perturbation that is localized in small scale that does not perturb the magnification. And just as a reminder here, that in case you may have forgotten already, the second derivative of the potential is what's determining the magnification. So I can have a relatively small scale perturbation that doesn't add significantly to the overall mass of the lens, that significantly changes the local magnification. Of course, if I were to have infinite telescope resolution and I could zoom in all the way, I would see exactly what I see in the gravitational imaging case. I would see my little halo causing some kind of very small scale distortion. It's exactly the same physics. The only difference is I can't see this resolved source here in the unresolved source lensing. So somewhere along the line of sight for this lens, for this image, there's a significant perturbation that's causing this to be demagnified. So that's my signal for the flux ratio anomaly method. And then the idea is that with enough lenses, we statistically distinguish between these scenarios. So I don't know in this case, maybe if my subhalo is very close to this one or far away, but if I have enough lenses, I can start to say the universe is probably clumpy or it's probably not clumpy. I can do a little better than that. I can say there's I get a lot of small perturbations, which would be, sorry everyone, which would be more indicative of CDM, or I have just a few large perturbations, which would be more indicative of warm dark matter, where I only have the more massive halos. So we get something about the mass scale of the perturbations and the probability distribution. So there's a couple caveats. This is all very promising, but of course, nothing in life is easy. So one of them is you have to choose the right lenses. It's really important to choose lenses that don't have a significant large disk. So this is an example of a lens I cannot use. This lens has a really large disk. These are the lens images here. So this lens can be entirely described without adding any dark matter perturbations, just with adding this baryonic disk. So it's very important that in the region of the lens images, we don't expect a significant baryon component. And so we really need to have high resolution imaging in order to select deflectors like this one that look very elliptical and that we understand pretty well by looking at things like the Virgo cluster. Another caveat is that the source must be large enough. Okay, so here's two images of the same gravitational lens. On the left, we have an image of this gravitational lens taken in radio. So this is a lensed radio jet. You can see the 4 images here. And then on the right, we have an optical image. So if we take an optical image, we're seeing light coming from the accretion disk of the quasar. What do we see? We see that here, the image positions are the same. I think I have that. The image positions are the same, but these magnifications are really different if you look in radio and in optical. And this is because of microlensing. The accretion disk of the quasar is small enough that I can be lensed by individual stars in the plane of the lens galaxy. Dark matter subhalos, on the other hand, are very large. The radio jet is very large and it cannot be affected significantly by stars. And I have something a little better than my cat analogy, but the idea is actually really the same. So microlensing, these are micro arcsecond perturbations. So if we take our little AGN here, our quasar that's producing the light we're seeing with our gravitational lens, and I make a magnification map of stars in the plane of the lens galaxy. Now, brighter areas here are regions that are more magnified, and darker areas are regions that are less magnified. This little thing here is about the size scale of the continuum emission in angular size. So what I can see is if my continuum source happens to pass right here, it will be magnified. If it happened to be right here, it won't be magnified. I can't tell the difference between that effect and a dark matter halo. So that's why microlensing is a real contaminant to us. We cannot have sources that are this small that are affected by microlensing. And I can tell you, I've looked at a number of gravitational lenses by now, and every single one of them, we see this microlensing signature. It's just very common to see the effect of these stars. So what happens with a larger source? Well, then I zoom way out. Now this green and blue are the same microlensing map, but my radio source is much, much larger. It's this orange circle, and you can see I'm averaging over those density perturbations, those magnification perturbations. So if I move my source a small amount, I'm only going to be ever sampling the average field of the microlensing. I don't worry anymore about whether I'm here or here. And so with this large source, I don't have to worry about the microlensing. So it's very important to have a galaxy that's elliptical, and it's very important to have a source that can't be microlensed. Of course, some people like microlensing and use it to study things like the accretion disk and the stars. So it's nice to have some of them on my team so they can help me avoid contamination. Okay, so here's where we are halfway through the talk. And so we've gotten the gravitational lensing is great, and hopefully have convinced you of the potential. Unfortunately, unmicrolensed, unresolved source types are really rare. So radio jets were the traditional one I showed you. 1999 and 2000, a couple of people used them to think about dark matter, Mao and Schneider, Dalal and Kochanik, but they're very rare. Only 7 are known. 2 of them contain disks, and no more are expected to be discovered until SKA comes online. But we've been able to make advances. And one of the ways we've made advances is by using a new source type. So this was originally proposed by Moustakis and Metcalf in 2003. So you guys are becoming like AGN experts. We learned about the radio jet, which is extended. We have the accretion disk, which is very small and microlensed. The narrow line region is another large extended region of the quasar. The benefits are it is this tens to hundreds of parsecs, which makes it milliarc seconds in size. So we're not concerned about microlensing. The nice thing is it's detectable in virtually all optically detected quasars. They almost all have narrow line emission that we can detect. And that's one of those virtuallys you say because like maybe one time I'll be wrong, but like every quasar, narrow line emission. The negative, and the reason people hadn't done this, is it requires you to get spectroscopy to identify flux only coming from the narrow line region. So I'll show you this. And again, this is all in the quest of doing these flux ratio anomalies to detect dark matter. So here is a quasar spectrum. So if we look at the quasar, unfortunately, these are all too small to be resolved by modern telescopes. The quasar spectrum, so if I just measure the spectrum of a quasar, I get this black line, and I get components in the flux coming from different size scales. So the continuum emission is driving this kind of tilt here, this continuous light coming from the accretion disk. I have very prominent broad emission coming from the broad line region, which is also unfortunately small enough to be microlensed. But then the narrow emission is coming from a quantum mechanically forbidden transition here. This is the O3 narrow emission. Since it's quantum mechanically forbidden, it's very improbable that it occurs. You only see it in very low density areas. So that's how I know this spectral feature is coming from a very large low density region. So if I can isolate the light coming from this spectral feature, and I can do it for individual lensed quasar images, then I have a new source that, unlike the radio, can be applied to virtually all the quasar lenses. And now I can expand my sample and detect dark matter in more systems. So I did this with Keck OSIRIS, which is an integral field spectrograph with adaptive optics. The adaptive optics, so the laser guide star adaptive optics, are absolutely essential for this. So this is a HST image of this lens. Here's the uncorrected version. I mean, it doesn't really matter that it's small, like, yeah, you cannot resolve it. But with OSIRIS, we get back that HST resolution. But importantly, every pixel here is a full spectrum. So we get all the wavelength information. So after doing some careful modeling, accounting for the point spread function, we can extract the spectra. So these are these quasar spectra for this guy. And then I fit the spectra and I measure the O3 emission. And for this lens, we do detect evidence for needing a perturber on top of the main deflector model. So I put down just a Monte Carlo with some different perturbers, and I allowed the mass of the perturber to vary. And this is just to get an order of magnitude estimate to our sensitivity to dark matter. Of course, we don't necessarily think the perturber has to be in the plane of the lens, but this was just our first lens. It was our proof of method. So we just did a simple mass scale. And we found that a perturber with mass order 10 to the 7 to 10 to the 8 could account for the flux ratio anomaly we saw from our measured forbidden line transition here. And so that's exciting because it's well within that regime where we think the majority of halos are starting to be dark. The other nice thing about this experiment is that this lens had also radio data. So we could really test our method against the previously validated methods. And we did find consistent flux ratios with what the radio emission studies had found. Another major thing that's happened recently is that we have a large number of new quad quasar lenses discovered in DES, Gaia, and Pan-STARRS. A major part of that has been the Graal collaboration, also members here at Heidelberg. And these lenses, combined with the narrow-line method, have let us really push this forward. So none of these guys, well, none of the new ones are radio loud, right? So we have to apply that narrow-line method to these systems. So in addition to Keck OSIRIS is great with the adaptive optics, but the adaptive optics are really limited. You can only do the correction in certain wavelength bands where the atmosphere lets you let the light through, but then also they're red enough that the adaptive optics is effective. So really just in H and K bands for those of you that are observers. So if we move to space, though, we can do a lot more lenses. So these are two programs that I was a PI of, using the GRISM now to do this measurement. And I show you this mostly just so you appreciate my suffering. Here we have a direct image taken with the Hubble Space Telescope, and this is what GRISM data looks like. So the light just gets dispersed along the X direction, and these little arrows are pointing toward where that narrow emission is. So I made a model. It fits all the different spatial light components iteratively with their own spectra. And using that, I was able to extract the narrow line fluxes here. So I've measured that for about eight lenses in this sample. So these are 8 new lenses that didn't have the radio. And so we were excited about this, and we said, moving forward, let's improve our dark matter model. All right, you're gonna have to bear with me before you hear dark matter results. So we have our 8 lenses. So now it's time to do more than just one perturber in the plane of the lens. It's time to do a full cosmological inference. Let's see how well we can measure the properties of dark matter. So I'm going to walk you through our model, and then I'm going to tell you our results. So instead of doing a simple one perturber thing like I did for that first lens I talked about, now we've motivated a full cosmological dark matter prediction. Let's take a look at a real simulation. So our simulation has halos all along the line of sight as well as in the lens. And then we have to trace those light rays all the way through all 4 of them for the 4 images. So here are some of the components of our model. It includes the mass function of halos bound to the main lens, the effects of things like tidal stripping and disruption on the halos that are in the main lens here, the subhalos. That's actually a major source of uncertainty for us. The spatial distribution of the halos, the mass function of halos outside of the lens, and the mass concentration relation. Unknown finite source size. So these are all things that we marginalize over in our sample now. It's much more realistic. All of these things have analytic functions that describe them that we sample from. And so here's just an example of how it all looks once you boil down to it. So our model proposes a realization of dark matter. It does the multi-plane lensing calculation, and you get something that looks like this face on. This is a convergence map, an effective convergence map. This is the equation for the convergence. It's roughly proportional to the magnification. So redder areas would be more magnified. And this has the main deflector mass profile subtracted. So that's why we're not seeing, all we would see if I didn't do that would be the magnification caused by the main deflector. But this lets us see these subhalos. And you see, because we correctly do this multi-plane lensing effect, we get these interesting arc shapes. This happens because a halo can potentially affect multiple physical regions if it's closer to the source. And this is a warm dark matter realization. This is a cold dark matter realization. So we simply take our observed image fluxes image positions and then use that to calculate the magnifications we would expect to see. And we do this many times. We use approximate Bayesian computing, and which I'm going to skip, but all of our software is open source and publicly available on GitHub. So that's a really nice thing if you're interested in doing either the realizations or the lensing calculations. So here's our result. So this is showing our constraint on the half mode mass of dark matter. And we find a 2 sigma upper limit on the half mode mass. In this field, 2 sigma is the convention. That the half mode mass must be lower than 10 to the 7.8 solar masses. And if it's a thermal relic, it has to have a mass greater than 5.2 keV. And you can see here, these are some of the parameters we marginalized over: the normalization. These are the ones I didn't even mention: the slope of the halo mass function, the normalization, and then here the half mode mass. And here's a more meaningful visual maybe. So this is cold dark matter here. Our purple line is here. So we've ruled out any dark matter model that has a turnover below this purple line. That's what our measurement has done with these 8 lenses. For comparison, the gray dashed line shows the Lyman alpha forest constraint from Veal et al. And then just as a reminder, this blue band shows where we estimate the transition from dark halos to satellite galaxies. So satellite galaxies we could have seen out here. Blue is where we think probably most halos don't contain stars. So we're really measuring the difference in these mass functions in the regime where we couldn't have done it with stars. We also combined our results with Milky Way satellites. So the red line here is our lensing measurement. The blue line here is the Milky Way satellites measurement. And the purple line here is the combined constraint. So what's nice is by combining our measurement where the host halo is a much higher mass than the Milky Way halo, we actually improve the constraint you would get just from the local group. And that's just with our 8 lenses there. And we've looked at some other properties of dark matter, which I'm going to go through a bit quickly. Things like the mass concentration relation. Normally people measure this from sort of 10 to the 12 to 10 to the 15 solar masses. This is a compilation. But of course, because we're measuring these low mass dark matter halos, we're sensitive now into this mass regime 10 to the 7 to 10 to the 9, orders of magnitude below where you can test it with other methods. We can also look at different formation mechanisms for the warm dark matter and look at how our half mode mass constraint maps onto many different production mechanisms. We took a look at primordial black holes, all with these lenses. And so we had to, because obviously you would get a lot of primordial black holes. In order to make the calculation feasible, we just simulate the black holes in the region around the lensed images. This brown line is our strong lensing constraint. So this is the fraction of primordial black holes versus primordial black hole mass. So you could see we're not, with this sample, doing better than something like X-ray binaries, but it is completely independent. And it shows that we have the infrastructure to do this. Another thing is particular models of self-interacting dark matter, where the dark matter, when it reaches a certain density, has a runaway collapse. So we can rule out some of these models. Importantly, in this kind of velocity dispersion regime that you can't test, for instance, with galaxy clusters, because our halos are so much lower density. We can also connect our power spectrum measurement back to the primordial power spectrum. Of course, our constraint is very uncertain. We have to be very cautious about how we try and make that mapping. But because it's at such a low mass scale, even though we have a very large uncertainty in the power spectrum, it maps into a very small uncertainty at early times. And I am excited to see what that gives us as we get more lenses. So for the last few minutes, I'm going to talk about another source for detecting dark matter. So we have these really nice results from the narrow line, but there's another way we can do this, and this is with the quasar warm torus. And this is the part of the talk about James Webb. So why would we use a different source if the narrow line is so magnificent? And this comes back to that cat here. So again, if we make the source even smaller than the narrow line source, then we can be more sensitive to lower mass dark matter. Also, the measurement should be straightforward without having to suffer and fit spectra. So the narrow line emission is this red line here. This is how much the flux ratio of an image changes as I move a perturber near a lensed image. So at 0, the dark matter is right on top of the lensed image. And over here, it's 1/10 of an arcsecond away. So you can see the red line, even if my 10⁷ mass halo is sitting right on top of my narrow line region image, then I get about a 3% flux ratio change. For the black line, though, the source size of 5 parsecs, I get a much bigger, a 10% change in this case. So having a smaller source makes me much more sensitive to individual low mass perturbations. And we think with the warm torus, it is in this 1 to 5 parsec regime. So we should be certainly sensitive to individual 10⁷ halo mass perturbers. And the more we can push that down, the more we can be sure that there really are dark halos, as well as testing these interesting different models of dark matter. So here's the anatomy of the mid-IR quasar spectral energy distribution. So here's a little simulation of a quasar torus. You have this cold torus on the outside. Oh, sorry, the warm torus on the outside. I was recently corrected by an AGN person. I've been calling this the cold torus, but they call it the warm torus now. So the warm torus, and then the hot torus is just on this inner edge here. So if we look at the spectral energy distribution here from about 1 to 10 microns, we see that we get some light contribution from here. This is coming from the quasar accretion disk, and we can verify this model here by doing things like interferometry and reverberation mapping of low redshift quasars. So you see the accretion disk here, but then we have light coming from this hot torus component. So I guess you could visualize that as like the inner region of this particular simulation. And then we have the warm torus. Wow, that's a typo. That should be milliarcseconds. That's an important typo. So that's starting out here around 4 microns, depending on the temperature, and really starting to dominate the spectral energy distribution around 10 microns. So these two things can be microlensed. This one should say milliarcseconds, and it's not affected by microlensing. It has to be large. And again, we can actually see this in low redshift AGN. That's how we know that it has to be extended. You really need rest frame 10 micron, observed frame 20 to 30 micron, depending on the source redshift, in order to be sure. Some people took a stab at looking at the hot torus, so 3 micron rest frame in 2013 and even back in 2000. So they're looking at 11 micron imaging from the ground. And that's very challenging because the atmosphere is warm. It becomes really difficult as you get even to 11 microns. It was promising though. These results were promising. They were consistent with the radio. It seemed like a promising method, but it really is limited to very bright sources. So I am leading a program with James Webb to measure mid-IR flux ratios with the James Webb Space Telescope, 31 systems. So we selected all known multiply imaged quasars, which were also detected in WISE. That way we could estimate our exposure times for James Webb. We require the image separation to be large enough that we could resolve all 4 images and to have no disk in the deflector. The program is going to take 43 hours. It's a medium program. We have 4 bands of imaging. That's to try and help us understand whether microlensing is occurring or not, or how contaminated we might be. And the exposure times are really short. It's just 1 minute in these 3 filters and about 10 minutes in the reddest filter. So why does it take 43 hours? Because it's so expensive to point Webb at a new target. So that's really all of our time is going toward like changing the filter wheels, dithering, and moving to our new targets. But we convinced the tech, so that was good. So here's our program status. This is just a subset of the lenses we're going to observe. Half of the sample so far has been observed. The program will be completed by 2024. And I'm almost done with the first system analysis. We expect our publication of our dark matter constraint from the first 10 lenses by the end of summer. I'll just give you some highlights about the first data. So here it is. It's so beautiful. Our 4 filters. And all we need to do, guys, measure the relative brightnesses of 4-point sources. Should be so easy. Of course, we have some challenges in the new observatory. It's really a new frontier. So one thing is things like the 0 points have not been characterized. Here's a nice email exchange I had or at the web help desk. So I'll read it in case you can't see it. I was wondering if there are any estimates of the 0-point uncertainties for MIRI, the instrument I'm using. Here we go. Thanks for reaching out. I'm not sure if you're asking about the AB to Vega 0-point or the photon conversion factor from data numbers per second to millijansies per steradian. For the AB to Vega 0-point, the answer is no. If you're referring to the photon pile, we do not have uncertainties either. So we do the best we can. What's really nice, I have to say, I've been working with them a lot. They respond very quickly. They're extremely helpful. So anyway, I'm still waiting on that. And of course, you have other things like the point spread function model is broader than expected. So this is the expected point spread function model based on ground-based testing of the optics. And this is my best fit to the point spread function model of that data I just showed you. And I don't know if everyone can see it, but it is significantly blurrier is what I would describe it as. It looks like it's been convolved with a blurred Gaussian. Here's highlighting the difference between the two. And I was trying to understand why. One of the questions is something called telescope jitter, which is just how much vibration it had. It just adds some random blurring in. So the PSF simulator lets you adjust the blurring. So if I adjust it, I get actually quite a good fit to the PSF. But then Marshall Perrin, who's in charge of the point spread function simulation, actually took a look at my data when the telescope was observed. And this vibration is showing the telescope, my actual telescope vibration during my observation. And you can see here, it can actually measure the mean jitter, which is 0.89 milliarc seconds. So my model predicts 7 milliarc seconds, a factor of 10 higher than can be explained by looking at the telescope jitter. What's really a fun fact, so this is coming from changing the filter wheel. We had 3 clicks to get to the right filter. So you can see the whole observatory is shaking more than an acceptable amount just from changing the filter wheel. Another cool thing about this conversation is it can be found on GitHub. So modern collaborations are just possible. You just email people, have a whole conversation. This happened within about 12 hours that we were able to rule out this explanation. So sadly, it's probably going to take a while to get an answer. So one of the things that they're looking at, because other people have seen this with other instruments, is detector behavior. So if you have a bright point source, the current nonlinearity solution, so the dotted line is what would be if everything was linear. You can see we get some nonlinearity as we approach saturation in the data number per second. And so some of these neighboring pixels in this measurement, so the orange and purple, here's an orange pixel, and here's the purple pixel, are deviating in weird ways from the nonlinearity. So I think that that all just needs to be characterized still. And that's probably what's leading to the blurriness. We estimate, and this is really just a gut feeling from the more senior observers in my program, maybe 10% uncertainty in the fluxes, the absolute fluxes. What I've seen so far is I vary the different models, I vary my point spread function model, I vary whether I include a deflector or not, closer to 1% on the flux ratio, which is the key thing for the lensing. So as I promised, not only do I measure these fluxes, I'm also looking at the spectral energy distribution. So I have my 3 components here. I have my continuum emission, my red line here is showing my hot torus component, and then blue is this warm torus component. I know it looks a little absurd to fit 4 data points to this model with like 3 different spectral components, but this is a fairly good approximation to what we see in real life. So with that caveat, we can see my 4 filter fluxes here for image A. And we can actually kind of get an inferred model temperature for the cold and warm torus component, or for the hot and warm torus components. What's nice is for this lens, it's at fairly low redshift. And we can see this band is really dominated by that warm component, which is extended. And we do see that the SAD fitting procedure gives us a similar warm torus flux ratio to what we saw in our Redis filter. I will not give you the official flux ratios yet because I'm hopefully in the next couple of weeks, we'll have submitted the paper to the archive and you can take a look. But given that precision, I can make a forecast for what we expect to see. So given that flux ratio precision, if it holds for the remainder of the sample, we expect to be able to confirm or rule out a turnover in the halo mass function down to about 10 to the 6 solar masses. So an order of magnitude lower than what we were previously able to do. For comparison, this is the limit for Milky Way satellites, and then this is the limit where about 50% of halos have galaxies. And then we've also made a forecast. This is a fun forecast. So if we have mixed dark matter, 50% warm and 50% cold, so but we pretend we don't know that. So the green line shows the input truth model. Potentially with James Webb, we would be able to detect that it was 50% warm and 50% cold. Of course, this depends on what you put in for your turnover in the halo mass function. In this case, the warm dark matter was quite warm, about 10 to the 8. But I think this is just to highlight there's like a whole new regime of models we'll be able to test. And of course, in the future, just in the next few years with LSST, Euclid, and Roman, we expect to find thousands of quasar lenses. We have new generations of detectors on the 10-meter telescope at Keck right now being developed, and also for the 30-meter telescope that will let us make this measurement rapidly and with higher sensitivity. And so I'm very excited for the future. And here is the talk for next week.
Okay, well, thank you very much. Actually, could you just put your slides back to your yeah, that's right. So we'll talk about this amazing technique. I mean, I've rarely heard such an incisive path to such a important result as you've presented today. I have to say that, and I'm sure that there will be many people both online and here wanting to follow up. So please put your hands up, first of all, from the hall. So Keith Delamont is the first.
Yeah, thank you for the nice talk. You showed the nice comparison between the cold dark matter and the warm dark matter, and you also mentioned that the warm dark matter model has as a parameter the mass of the particle, right? Right. So the fact that you can tune that mass of the particle, essentially, how much does it, I mean, will you then be able to say, well, it is warm dark matter or it is cold dark matter, or will you be able to say, you know, it is this mass of the particle?
Oh yeah, that's a really good point. So I kind of oversimplify things when I talk about it. We really can only measure right now in our models the half mode mass. So I'm just trying to go back to this slide. This is 4 different sterile neutrino models, and here on the x-axis is the mass in kilo-electron volts of those sterile neutrino models. And these are all models, these are all upper limits based on our single half mode mass measurement. So we measure this empirical half mode mass or a turnover, but then the mapping to the actual particle mass is much more complicated. And so there's a definite degeneracy between which model you assume to be correct and our half mode mass estimate. So I'm really glad you asked that. Thanks.
Okay. Another question from the hall.
So about primordial black holes, you gave some statements, some quick statements. For instance, could it be useful to use the James Webb to try to measure lensing from our own galaxies or large magnetic LMC, large magnetic cloud?
Oh yeah, so I think the optical setup of our lensing, we're not going to see lensing in our own galaxy happening. As far as I know, I think that the Einstein radius for a primordial black hole in our galaxy would just not be the right size given the optical setup. But I assume other people could do other experiments with other lensing, like we've done with Kepler, to maybe look for these primordial black holes. I don't know if anyone has a plan for that with James Webb.
Okay, thank you. Oh, let's Joachim first. I'll check your mic.
Very interesting work. I'm particularly excited by this 31 JWST observations you get. Now, you said due to these flux uncertainties, to the 0-point uncertainties, the individual flux measurement is accurate to 10%. but the flux ratio you can get down to 1%. So how does this come about?
So in a given filter, all of the flux ratios will scale up and down by 10. All of the fluxes might scale up and down by 10%. So I don't know if I'm measuring, you know, whatever. Yeah, I can go up and down. But if I just want to know A to B, that ratio, I don't have to have a particularly good even point spread function model to be able to measure the ratio of the image fluxes, right? And so they all just scale up and down together.
It's just the absolute fluxes, but the relative fluxes in the same exposure are
Exactly. We so far, based on our testing, the absolute flux is quite uncertain, but the relative flux between two things in the same image is, we think, very well constrained. Yeah.
Also ask a question about the relative fluxes. You mentioned that you only had very small exposure times due to most of the time being taken on overheads. But you also showed a plot showing the detector responses changing. And I wondered if the different timescales for changing the detector response for different illuminations would be the main uncertainty preventing you from making more precise flux ratio measurements. It's a question of the timescale for the detector to sort of equilibrate with the time that you're on source.
Yes.
And would there be also different observing techniques or a special way of observing where you could minimize this effect?
I think that's really interesting. I think, right. I'm interested to see, as we characterize the detector, like we have with Hubble, now there's very precise ways to deal with all of these effects, and people have really come up with that. And off the top of my head, I know that they've seen the 0 point within it has some significant fluctuation just from exposure to exposure with James Webb. That really is important for faint sources. Our sources are so bright that that level of the reset uncertainty is probably not important, or would just affect all of them together. What I am, and actually just occurred to me making this talk today, wondering is something like this effect with this point spread function. I would like to investigate. I showed the effect of the neighboring pixels affecting each other here. It occurs to me that since this alters the shape of the point spread function, if I have a brighter source, it might alter it differently from a fainter. And so I need to characterize how much the point spread function changes as a function of flux.
What time scale is it? Is one frame here?
I think it's 3 seconds.
So these are actually, you know, quite long time scales.
Yeah, I mean, and what's more relevant to me, so my exposure time, I have maybe five frames, but I get up to about 40,000 counts in that time frame.
All right, yeah.
So I'm well away from actual saturation, which seems to occur around 50,000, but I am in sort of this nonlinear regime.
No, I was just wondering if you had lenses where you had a 10:1 ratio.
I do,
something like that.
I do, and
that might be an effect here.
I think absolutely for that one, that's exactly what I thought of just a couple hours ago making this talk, that I better check that out. Yeah.
Okay, fascinating.
Yeah.
Fascinating.
Yeah.
But I'm sure that this will be solved.
I'm sure that it'll be characterized to arbitrary precision at some point. And so the key is making sure our estimate of our uncertainties is big enough for this paper. I think that's what I'm worried about.
So let's now thank Anna for this very, very incisive, interesting, and fundamental, if I may say so, presentation. Thank you very much indeed. Yeah.